Hello, welcome to 5.5, Bases Other Than E and Applications. So you probably are thinking, okay, well that natural log or that base E, that's pretty cool, but what happens if it's something else? What if it's a 2? What if it's a 5? Well, here we're going to talk about that. It's the definition of an exponential function to base A. If A is a positive real number where A is not 1, and x is any real number, then the exponential function to the base A is denoted by a to the x. That's fine. We're good with that. And it's defined by, here we go, a to the x is e to the natural log of a times x. So you can redefine any other base to a base e for the derivative purposes. If a is 1, then y equals 1 to the x, which is 1, and that's a constant function. It's not exponential. The definition of a logarithmic function to base a, I'm sure you've seen this. You've probably seen both these in your pre-calculus days, but maybe not defined this way. If a is a positive real number, where a is not 1, and x is any real number, then the logarithmic function to the base a is denoted by log base a of x, and is defined as log base a of x is 1 over the natural log of a times natural log of x. And this utilizes the change of base formula. The log base a of x is log base b of x over log base b of a. What we're just using is the log base e as our base, which is natural log. Now that's what I'm talking about down here. It says the textbook does not state it explicitly, but the above change is the change of base formula. That's what I've just done here. So, properties of inverse functions. If y equals a to the x, y equals a to the x, if and only if x equals log base a of y, and a to the log base a of x is x, and log base a of a is x. So write the exponential equation as a logarithmic equation. Okay, so our base here is 27, so this would be log base 27 of 9 equals 2/3, because we're saying 27 to what power is 9? 27 to the 2/3 is 9. Same thing here. Log base, what's the base in the exponentiation is 16 of 8 gives us 3/4. That's saying 16 to the 3/4 is 8. Go on to the next page. It says solve the equation accurate to 3 decimal places. 3 to the 2x equals 75. Natural log of 3 is 3 to the 2x is natural log of 75. Power comes out front. 2x times natural log of 3 equals natural log of 75. If I divide both sides by 2 natural log of 3, then x equals natural log of 75 over 2 times the natural log of 3. And that's going to be 1.965. Next one, log base 2 of x minus 1. You do 2 to the power of log base 2 of x minus 1 equals 2 to the 5. Log base 2, and the 2 being that base there as the power, for the power part, that means x minus 1 equals 2 to the 5th, which is 32. Adding 1, x must be 33. So 5.13, derivative for bases other than e. So the derivative with respect to x of a to the x would be natural log of a times a to the x. Just remember that it was a to the x equals e to the natural log of a times x. So this is just a coefficient. So if you took this derivative here, you'd have e to the natural log of a times x times the derivative of the power, and that's our natural log of a. Well, then this power can be re-expressed as a to the x times natural log of a. So the point is, you can think of this as a general formula for the derivative of an exponential And then if a is e, natural log of e is just 1. That's another way to think about it. The derivative with respect to x of log base a of x is 1 over natural log of a times x. The derivative with respect to x of a to the u is natural log of a to the u du dx. And the net derivative with respect to x of log base a of u is 1 over natural log of a times u du dx. Let's scroll this up. Let's find the derivative of the function. So y prime is going to be, we got a product rule, so it's x times this derivative plus the derivative of x times 6 to the negative 2x. So y prime is going to be x times, so this derivative is going to be negative 2x. No, sorry. Natural log of 6 times 6 to the negative 2x times the derivative of negative 2x, and that's negative 2. There we go. Plus 1 times 6 to the negative 2x. So y prime is going to be negative 2x natural log of 6 times 6 to the negative 2x plus 6 to the negative 2x. So you could factor that out if you wanted to. You don't have to. It'd be 6 to the negative 2x times negative 2x natural log of 6 plus 1. For b, h of x equals log base 3 of x times the square root of x minus 1 over 2. I'd split this up and call this log base 3 of x plus 1/2 log base 3 of x minus 1 minus log base 3 of 2, and that one's just a constant. So our h prime of x is going to be 1 over the natural log of 3 times x, for this part, that base here, plus 1/2 times 1 over natural log of 3 times the quantity x minus 1 minus 0. And that 1 over natural log of 3 is a common factor here. You could factor that out if you wanted to.
Good morning.
Hey.
I'm like ignorant.
Okay. If you wanted to, you could take this a step further and combine these two. This becomes 1 over natural log of 3 times 1 over x times x minus 1 over x minus 1 plus 1 over x minus 1 times x over x. And that would give us 1 over natural log of 3 times x minus 1 over x times x minus 1 plus x over x times x minus 1. And that's 1 over natural log of 3 times 2x minus 1 over x squared minus x. Yeah, and these answers, I take this one, I take this one too. Oh, I forgot the 1/2, didn't I? There should be a 2 down here. And so should have a 2 on that part, 2 on that part. It's 2 up there. So it'd be 2x, so it becomes 3x on top minus 2 over 2x squared minus 2x. Okay, I think I got it all covered now. Move out of the way. Feel free to pause if you need a pause. We're going to go on to example 4. It says Find the equation of the tangent line, you can't read it yet, can you? To the graph of the function at the given points. So y equals 5 to the x minus 2, and the point is 2, 1. So what's our derivative going to be? 5 to the x minus 2 times the derivative of x minus 2, which is just 1, times the natural log of 5. Now at 2, 1, y prime of 2 is going to be 5 to the 2 minus 2 times natural log of 5. It's 5 to the 0 times natural log of 5, which is just natural log of 5. We're working off the point slope formula, y minus y1 equals m times x minus x1. So y minus 1 from here equals natural log of 5 times x minus 2 from here. So y minus 1 equals natural log of 5 times x minus 2 natural log of 5. Then we'll add 1 to both sides. Y equals the natural log of 5 times the x plus 1 minus 2 natural log of 5. That'd be the exact value for the equation, tangent line at this point. Now note, we're going to talk about integration. Integral of a to the x dx would be 1 over natural log of a times a to the x dx, because the derivative would have produced a natural log of a as a coefficient being multiplied. So it would be divided by that when we do the integration. Which brings us to example 5. So this integral is going to be 1 over the natural log of 5 times 5 to the negative x times negative 1, because this power, its derivative would have been negative 1, so you multiply or divide by negative 1 in the end, plus some constant c. So it becomes negative 5 to the negative x over the natural log of 5 plus some constant c. And you could move this down as well. You could call this negative 1 over 5 to the x natural log of 5 plus c. But I would take both these answers. Down here, the power rule for real exponents. Let n be any real number, and let u be a differentiable function of u. The derivative with respect to x of x to the n is n times x to the n minus 1. And the derivative with respect to x of u to the n is going to be n times u to the n minus 1 du dx. Now we get to talk about the next page, which is it page 4? Applications. That translates into word problems. Now, you probably remember, I'm hoping, hope you've seen this before, the limit definition for E. And we did this back when we were talking about finance. We're talking about computing, trying to find continuously compounding interest. So A equals PE to the RT. That formula is derived by the compound interest formula if we take it as n goes to infinity. I mean, here's the definition for E, one of the definitions for E. Its limit as n goes to infinity of 1 plus 1 over x to the x, which could also be written as the limit as n goes to infinity of x plus 1 over x to the x, and that's our E. So what I want to just show you here is, this is from your pre-calc days, and we talked about taking your compounding period going to infinity. And here we define x to be n over r, so x goes to infinity, 1 plus 1 over n over r to the n over r times r. So it's going to be p times the limit as x goes to infinity, 1 plus 1 over x to the x. That's where I made the substitution here. So I think I should have kept this part as an n still. And then you get your P e to the r, and then we have time on the outside of this. So that's our formula for continuously compounded interest. So our summary of compound interest formulas: let P equal the amount of the deposit, T is the number of years, A is the balance after T years, and R is the annual interest rate in decimal form, N is the number of compounding periods per year. And this is the most common type of formula. I have seen it where N is the total number of compounding periods, but that tends to be more work. So A equals P plus 1, P times 1 plus 1 over R to the NT. This is our regular compounding formula, and as we saw above, it derives into this if you take N to be infinity. Okay, compound interest. Consider a deposit of $100 placed in an account for 20 years at rate R% compounding continuously. Use a graphing utility to graph the exponential function, giving the growth of the investment over the 20 years for each of the following rates. Compare the ending balance for each rate. Okay, so we have didn't type in the rates. That's not very good. In the first case, the rate is 3%. So the amount is going to be $100 times e to the 0.03 times t. And for t being 20, we have a equals 100 times e to the 0.03 times 20, which is $182.21. And this shows that growth. In our second case, we're at 5%. So a would be 100 times e to the 0.05 t. A is 100 e to the 0.05 times 20. And that's going to give us $271.83. It's a steeper growth there. Let's go on to C. For C, it's even steeper growth, and we're talking about 6%. So A equals 100 times e to the 0.06 times t, which is 100 e to the 0.06 times 20. And that's going to be $332.01. So a bigger increase. As you'd expect, greater percent interest, the greater the increase. Let's go on to our last page for this section. Learning theory. In a group project in learning theory, a mathematical model for the proportion P of correct responses after n trials is found to be P equals 0.86 over 1 plus e to the negative 0.025 n. First thing, find the limiting proportion of correct responses as n approaches infinity. We're looking at the limit as n goes to infinity of 0.086 over 1 plus e to the negative 0.025 n. That'll be 0.086 over 1 plus e to the negative 0.025 times infinity. 0.086 over 1 plus 1 over e to the negative, well, now it's positive, 0.025 times infinity. It's 0.86, not 0.086. 0.86 over 1 plus 1 over, this is infinity. 0.86 over 1 plus 0. 0.86 over 1, which is 0.86. So as n goes to infinity, they should be getting 0.86 or 86% of them correct. Find the rates at which P is changing after n equals 3 trials and n equals 10 trials. So for B, I'm going to scroll this up a little bit. going to erase this part. Okay, so our dp dt, or p prime, is going to be this derivative, 0.86. Let me back up. Let me redefine p. Rewrite it this way if it's easier to see it. 0.86 times 1 plus e to the negative 0.25 n. So that p prime would be 0.86 times, now this derivative of 1 is 0, the derivative of e is going to be e to the negative 0.25 n times, they should be dp dn, not dp dt, times negative 0.25. Oh, I have this written wrong. This is to the negative 1 power. Okay. So this should be 1 plus e to the negative 0.25 to the negative 2 power times negative 1, because that was the power, and then times the derivative of what's inside. That's 0 plus e to the negative 0.25 n times negative 0.25. So our p prime is going to be, negatives are going to cancel, 0.25 times 0.86 times e to the negative 0.25 n over 1 plus e to the negative 0.25 n squared. This works out to be 0.215 e to the negative 0.25 n over e to the negative 0.25 n squared. Now we're going to plug in 3 for n and 10 for n. So we're talking about, this is the rate of change, the rate at which it's increasing or decreasing. It should be increasing with more trials. So at what rate is it increasing as the trials go on? So what's the rate that's increasing after 3 trials and the rate of increasing after 10 trials? So p prime of 3, I'm putting 3 in place of the n's. In this case, we have 0.0468, which is approximately 4.7%. That's the rate it's improving. Now p prime at 10, that's 0.215 e to the negative 0.25 times 10 over 1 plus e to the negative 0.25 times 10. That's going to give us 0.015, which is about 15%. It's a 15%. The rate of increase is 15%. So the rate of increase of performance is 15% after 10 trials. Okay, well that'll do it for 5.5. Wow. And send me your questions. Thank you.